Hello, class. This will be the recorded lecture for section 4.4. We're going to finish it by focusing on a maximization problem using some geometry. Kind of near and dear to my heart. My grandfather was, on my father's side, had this big garden when I was growing up. Great food came out of that garden. And he always had to put a fence up because he lived in an area where there were deer and rabbits were bad for the garden as well. And so it always reminds me of my grandfather when I talk about this particular problem. And so what we'll do is use some of our newfound modeling ideas with quadratics to solve this problem. And this one basically says we want to maximize an area with amount of fence that we buy. So you say like you go to Home Depot and you say, I want 1,600 yards of fence to enclose a rectangular field. So what would be the dimensions of the rectangle that encloses the most area? Why do you want the most area? Because that's where the capability of planting the most crops or the most flowers, if it's flowers, whatever the case may be. And so the best way to do this is to definitely do a sketch. And so if we do this sketch, it would look like that rectangle. And we're not going to do anything more advanced than a rectangular figures. The process is the same. If you get into calculus, you'll be able to do more complicated ones like cylinders and things like that. I do a problem in calculus where we maximize the volume of a can of soup, and that you need a little bit more tools like a calculus to do that. So if we define this rectangle as the width and the length, what do we know? Well, the first thing we know is that the area of a triangle is W times L. And so we were also given that there was 1,600 yards, of fence. So with that information, what do we know? Well, remember that in a rectangle, across the two lengths are equal, and then the two widths will be equal. And so we know that if you add all that up, that should be 1,600 yards. If you remember from your geometry days, that was called a perimeter around a particular figure. And so we would have 1,600 equals, we have two W's, right? Plus two L's. So now we have two equations and two unknowns, so that's good. And so what we want to do is maximize A. What do you think the strategy is? Well, the strategy would be we want to put A into a single variable because we have two of them now. We have W and L. So we could use the perimeter equations to solve for one of those variables and then plug it back into the A equation. And so let's do that. Let's just solve for L. So I'm going to bring the 2W to the other side, and you would get 2L is 1,600 minus 2W. And if you divide each side by 2, you would get L equals 800, right? Minus W. So now we know that L equals 800 minus W, so we could get rid of the L in the A equation and plug in 800 minus W. So you see when we do that, it would be W 800 minus W. Continue that, you would see that. Guess what kind of equation we get? Well, if you didn't guess it was a quadratic, you haven't been paying attention in what section we're in, which are quadratics. But here we end up with a quadratic. And we have the A value that's less than 0. So it points down, or opens down, excuse me. And our vertex is our maximum. So to get the maximum area, let's find the vertex. Well, the vertex is minus b over 2a. And our a value would be minus 1. And our b value is 800. So when you plug that in, you get minus 800 over 2 times minus 1. And so you would get a value for W of 400. And you go, okay, so how do you find L? Well, we have the equation already set up for L, and we defined it right here, right? And so when you plug 400 in for that equation, L would be 800 minus 400, and that also equals 400. And so this would be 400, this would be 400, this would be 400, and this would be 400. So what did we just prove? That the maximum area of any rectangular figure is a square. And so how do you find the total area? Well, the area is 400 times 400, or 400 squared. And that would be 160,000. And this was yards, so that'd be 160,000 square yards. That's A max. And so I believe I have a little graph here to show you. So let me show you this. I got this right out of the book. And so with regards to what it would look like, the vertex would be 400 and then 160,000. And you could see that if we were at 0, 0, we would have 0 area, right? And 800 is the other one where you have 0 area. How does that work when you think about the equation? Well, let's go back to the equation here a little bit and take a look at it. So I need a little bit of space here. So let's. Okay, so here is our area equation, right? Well, what is our x-intercept? Well, it's already factored for us, right? The x-intercept would be W equals 0, or 800 minus W equals 0. So W would equal 800. So again, just like when we were talking about that revenue equation, using the demand function and finding the two extremes, that would be the domain of this particular real world problem. Is that if you looked at the graph again, you could see that our two intercepts, again, start at the origin, and a lot of the time, real world applications start at the origin, and you can see it stops there. And if you think about it, if the width, in this case, the x value is 800, 800 plus 800 is 1600, right? So if you have all the fence in the width, there's no length, and 0 times 800 is 0. So that's how you kind of rationalize that. What I'm going to do now is one more problem that's not in the slide. And so what I'd like to do here is to do another problem that's very similar, but we're just going to change one attribute of the fence problem. And so what I did here is pause real quick and wrote the new problem here on the whiteboard. So here's a problem where we're going to use, say like this is a little river that runs by your property, and you decide to put up a garden, and you're going to use the river as one part of your fence. And that's kind of smart, right? Because you want to try to maximize the amount of area and minimize the amount of money you have to spend on a fence. And so if you think about it, let's do that same problem, but now you go and get 1,600 yards of fence from Home Depot. And in this case, we only have 3 sides to the fence. And so that's why it's nice to do, say like we call, let me use green here for the variables. So say like we call this W, right? So then this side has to be W, and we only have one L. And so when you set up the perimeter equation, you would get 1,600 equals 2W plus 1L. And the area is still the area. It's the width times the length. So again, when we do our calculation, first thing we do is solve for one of the variables with the perimeter equation. In the perimeter equation, let's solve for L. That would be the easiest one. So L equals 1,600. Bring 2W to the other side, you get minus 2W. Plug it into the equation. You get W, get rid of the L, is 1,600 minus 2W. And so that would be 1,600 times W minus 2W squared. And again, the A value is negative. So the vertexes are max. The A is minus 2. The B is 1,600. And so the width of the vertex would be 6 minus B. That'd be minus 1,600 over 2 times A. And so you could see we get again 400 yards. So, but what's interesting is what is L? L is 1,600 minus 2 times 400. So L is what? 800 yards. And that is quite interesting in the fact that L is twice the length of the 2 W's. And if you think about it, you say to yourself, that makes a lot of sense, because if you're using the river as one side, you want to maximize the amount of free fence you get, right? And so what ends up happening when you try to do that maximization problem, it ends up being that the river, which is one of the lengths, will end up being twice the length of the other two, which is the width. And so that will end this lecture on section 4.3. There is quite a bit of other topics that are in section 4.4, section 4.4 that we're just going to skip. I think if you had a good understanding of the 3 modeling aspects that we talked about, number 1, profit, cost, and revenue combinations using quadratics. Number 2, revenue with a demand equation. And number 3, maximizing area using the rectangular figures.